So now I want to say a bit more about the argument Euler used for the Königsberg bridge problem. And so the idea is like this, with a network, got some nodes in the kind of A1 up to AN. So in the Königsberg problem, these were just the land masses that had the bridges between them, and we have and then we have edges between the nodes. So in the Königsberg problem, the edges were bridges, but when people discuss this kind of thing more abstractly, they normally talk about edges. And the number of edges meeting AI is going to be DI, right? So each edge runs between two different nodes, and for each node we count how many edges are incident on that node, how many other nodes that node's joined to, and that's numbers called DI. And our question is, let's write it down. So is there an so-called Eulerian Tor, or Eulerian circuit? Let's call it a Tor, actually. Crossing each edge precisely once. Okay, and then and so Euler's theorem is that firstly, all DI are even. Well, maybe a circular Tor. Okay, so we didn't prove anything about, didn't prove any positive results so far. We haven't proved that there actually exists a Tor in this case, but we haven't excluded it. There might be a Tor, but it would have to be circular. If 2 DI are odd, and the rest are even, then there may be a Tor starting at one odd node and ending at the other. Again, we haven't proved that there is, but at least there might be. But, the real meat of the statement is part 3, that in all other cases there's no Tor. Okay. So I'm not going to write down the logic. The logic's the same as we discussed previously in the notes for the Königsberg problem. But we can just talk about it. Okay. So the idea, and then we'll have on the next board we'll have some examples to illustrate the situation. So what was the logic? Okay. So if you've got if you do have an Eulerian Tor, then you look at each node. It gets visited a bunch of times. If it's in the middle of the Tor, then it gets and every time you visit along one edge, then you have to leave along a different edge. So you join it. So that means you group all your edges in pairs, and so you must have an even number of edges incident on that node. So that's how it works for every node, except that it might be different for the beginning node and the end node. For the beginning node and the end node, well, they might be the same if you've got a circular Tor, and then in that case, the same sort of logic shows that the DI has to be even. But if the beginning and the end are different, then you have if you start at DI, then you might visit it a bunch of times in the middle of the tour. In that case, you get pairs of bridges for that, but then there's an extra one for the first step of the tour, so you end up with di being odd. So that was the logic for the Königsberg bridge problem. And as I say, in a second we'll do some more examples. Okay, so here's our first example. We're going to have 6 nodes. So we're going to do node 1, node 2, node 3, 4, 5, and 6. These are so n is 6. Our nodes A1 up to A6 as indicated here. And then we're going to have some edges. Okay, so let's draw the edges. Okay, so so now we need to count the edges. So what's the count of edges here? So each of these nodes has precisely 2 edges attached to it. Right? So here we've got D1 up to D6. They're all equal to 2. And so the first clause of our theorem says that maybe there's an Eulerian tor. But of course there isn't, right? Because there's no way you can cross over from this left-hand triangle to the right-hand triangle. There's no edges between them, so any tor either has to stay in the left half or the right half. So that's an illustration of the fact that I said, we hadn't actually proved anything about when tors actually do exist. We've only proved things about when tors don't exist. Okay. So that wasn't very interesting. But let's just modify this diagram a bit. So we're going to put in some extra edges. Now, this plot here is not valid anymore. So let's start marking up the degrees, the number of edges for each vertex. Okay, so here obviously we've got 3 edges attached here, 4 edges attached here, 2 here, 2 here, 4 here, and 3 here. Okay, so what does the theorem tell us? It tells us that in this case, right, we've got 2 odd degrees and the rest are even. So it says that there might be an Eulerian tor, and in fact there is in this case. Let's just draw it. So we can start here and go down this way, and then we go across to here, and up to here. Across this way, down this way, over here, up this edge, along this edge, back down here. Right? And now we've crossed every edge exactly once, okay? And that's an Eulerian tor. Okay? So let's just write what we had here. So we had So as the theorem says, in this case, we've got precisely 2 odd degrees. Well, the only kind of tor that you can have is one that starts at one of the nodes with an odd degree and ends at the other one. Okay. So that's our first example. Let's do another example here. So this is a kind of similar thing. We're going to have we're going to have a similar network of triangles. Now notice actually I started off by numbering these nodes here 1 up to 6, but that didn't really come into the argument at all. So at least I'm not going to bother naming the nodes this time. I'm just going to draw some triangles. Let's look at this this network like this. We want to know whether there's an Eulerian tor or not, so we have to again count the degrees. Okay, so there's degree 2 here, and everything's symmetric, so we can mark it there. And then here we've got degree 3, and similarly over there is degree 3. Here is degree 4. Here's degree 2. And what about these two here? 1, 2, 3, 4, 5. So that's degree 5. And that's degree 5. So the conclusion here is different. So we've got 5 odd degrees. So 4 odd degrees, so 2 3s and 2 5s. So there's no torr here. And we'll do clean the board, and then there'll be one more example in a second. Okay, so here's our last example. We're going to have an inner triangle like this. And then we're going to have an outer triangle. It's going to be bigger and the other way up. And then we're going to have some edges that will join the inner triangle and the outer triangle. Like this. Okay, so now we need to calculate the degrees. The main criterion for this theorem. So here we've got 1, 2, 3, 4. Here 1, 2, 3, 4. Again, all the outer ones are 4, and then it's the same with the inner ones, right? 1, 2, 3, 4 edges there. And, okay, so so every vertex has degree 4, and so according to the theorem, there might exist a circular torr. Right? There can't exist a non-circular torr. If you had a non-circular torr, then the two end vertices would have to have odd degree. But it's possible to have a circular torr, maybe. Okay? Haven't proved that, but let's just try and find one. It's not super trivial in this case. It might take you a few minutes, but let's just do one here. Okay, so what we're going to do, we're going to start by going along this first edge here. Let's mark it 1. That's our first thing we're going to do. And then we're going to go up this edge here. And come back down this way. Back there again. Then, well, there's nothing. We don't really have any choice about the next step. We have to come into the inner triangle. And then go along here, that's 6. And this way is 7. Back up to here, that's 8. Down this edge here, that's step 9. And we go up this edge here. That's going to be step 10. Down to there is step 11. And finally this way, step 12 gets us back to this node down in the bottom left, which is where we started. Okay, so sanity check, of course, we had 6 vertices, each of which had 4 edges. So you might think that makes 24 edges altogether, but each edge is counted twice, once for each end, so it's really 12 edges. And yeah, and here we see we numbered these 1 up to 12. We crossed every edge exactly once.